Hello, chemistry students. This is Mr. Sheldrup, and we're going to be walking through the part 1 of our molar conversion notes. Now, before we actually jump into any calculations, we need to get a few vocabulary terms out of the way. Now, generally, we're going to refer to things as particles, and that's the broad term. We want to actually get a little bit more specific if we can. And there's 3 different subtypes of particles: atoms, molecules, and formula units. If we use the word atoms, we're referring to unbonded elements. So these would be elements by themselves. Examples of this: carbon, right? If we're speaking of specific things, magnesium, iron, these are elements that exist naturally in single units. If we talk about molecules, these are going to be bonded elements. And it's going to be the same for both molecules and formula units. It just depends on which types of elements are actually in those bonds. If we're talking about molecules, these are covalent compounds. So these are going to be molecules that only exist of nonmetals. Now that includes the diatomic. So I could have covalent compounds and the diatomics. And remember your 7 diatomic elements: hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, and chlorine. Now when we talk about formula units, these are bonded elements that contain a metal. So these are going to be ionic compounds, metal with a nonmetal. We also lump acids in here. Acids have hydrogen, which kind of acts like a metal because it has a positive charge. So we'll count acids as formula units as well. Now, the first thing we do before we actually jump into any conversions, if we're ever talking about a mass, if we're looking at converting between grams, we'll always use the molar mass. And this is a value that comes directly from the periodic table. Our periodic table has all of the molar masses organized by elements. And the definition of molar mass, this is the mass of 1 mole of a substance. So if I were to have 1 mole of whatever element we're looking at, the periodic table will tell me what the mass of that mole is. And it always gives me a value that's 2 decimal places. Now, different periodic tables go to different levels of detail. Our periodic table, always 2 decimal places. So if I pull up my periodic table here, I see all my elements arrayed here. If I look over on the right side, carbon, element number 6. The number directly below the element symbol, the C, gives me 12.01. That's my molar mass. So what that tells me is that if I have 1 mole of carbon, that's equal to 12.01 grams. So this gives me an easy conversion factor to be able to use, and I can look this up for any element. Now it gets a little bit tricky if we talk about a compound. If I have something like H2O, I have to add up the H's and the O's. Hydrogen is 1.01, but there's 2 of them, so I have to add 2 of those together, plus oxygen, which if I scroll over a little bit is 16.00. If I add all that up, I get 18.02 grams. So if I have a more complex formula, I just have to add the individual molar masses together. Now, typically we refer to this conversion factor as grams per mole. So typically I would say carbon has a molar mass of 12.01 grams per mole, which tells me that that 12.01 grams equals 1 mole in my conversion factors. So let's actually jump into some of those conversion factors. Today we're only going to look at 2, and they're connected by this unit, this idea of 1 mole of a substance. So if I'm using 1 mole as kind of my go-between conversion unit, I can either convert that into a number of particles, if I were to actually be able to count how many of the individual particles of that substance I have, or I can convert between 1 mole and the actual mass of that substance. If I throw my sample on a balance, how much is it going to weigh? Now, for mass, we're always going to use the unit of grams. For particles, we're always going to use either atoms, molecules, or formula units. So these are going to be the units that we reference most often. Mass is always grams, and moles, we just use the unit mole. Now, if I'm doing a conversion between mass and moles, I'm going to use that word we just talked about, the molar mass. So I'm going to use the molar mass for that substance. And this gives me a number that has an infinite number of sig figs as far as we're concerned. Our periodic table always goes to 2 decimal places. So we're going to assume that that is a fixed quantity. That is a set number. That is not a measurement that we made. So that is not a number we're going to use to round our final answers. We just kind of ignore it in terms of significant figures. Now, whatever that number is going to be the units grams per mole. And all I have to do is look that up from the periodic table. So if I'm doing a conversion, I just look up whatever that element is on the periodic table to get its molar mass. Now, when we go between moles and particles, it's always going to be Avogadro's number. This is a set number. This number does not change. It is also going to be considered a constant, which also makes it infinite sig figs for our rounding purposes. So for significant figures, we ignore molar masses. We also ignore Avogadro's number. Avogadro's number is always 6.022 times 10 to the 23rd particles equals 1 mole. So that becomes our conversion factor. That many particles per mole, how we can go between particles and moles. So let's actually do a couple of these together. It says how many particles and what type are in 3.2 moles of neon gas. I always start these problems with my given. So I'm going to start with 3.2 moles of neon, and neon is abbreviated Ne. And I always like to put that number over 1. Let me fix my handwriting here a little bit. Now, 3.2 has two significant figures, so this is going to be important when we get to the end of the problem. I'm just noting it now because that's the only given number in the problem. What I want to do is multiply this number by a conversion factor to cancel moles of neon. And what I'm trying to get this into is particles of neon. So my conversion factor is going to allow me to go between moles and particles. And if I look up at the top, the conversion factor between moles and particles is Avogadro's number. Avogadro's number tells me that for every 6.022 times 10 to the 23rd particles, that's always equal to 1 mole. Mole would cancel out, and I could plug this into my calculator and solve for the number of particles. So I'm going to grab my calculator, drag it over here. I'm going to type in, let's see here, 3.2. All right. So I type this number into my calculator, and I get an answer of 1.927 e to the 24th, so times 10 to the 24th. This is where I have to keep track of the number of significant figures. We said 3.2 started with two significant figures. Avogadro's number does not count towards my significant figures. That's infinite significant figures, so I don't use that for my rounding rules. So when I round my final answer, I need to maintain the fewest sig figs from my initial problem, which is going to be 2. So when I look to round this number, my final answer is just going to be 1.9 times 10 to the 24th. Now, instead of the word particles, I want to use the specific type of particle that applies to neon. Neon's an unbonded element. So I'm going to use the word atoms. So my final answer, 1.9 times 10 to the 24th atoms of neon. All right, let's move on to another. What is the mass of 0.35 moles of aluminum sulfate? 0.35 moles. I'm going to write out the formula for aluminum sulfate. Aluminum's a +3, sulfate, SO4 with a -2, which means I need 2 aluminums and 3 sulfates. I'll put that all over the number 1. Now I'm trying to get this into mass. So what I first have to do is look up on the periodic table, what's the molar mass of aluminum sulfate? So I'm going to find aluminum on my periodic table, 26.98. So I'm going to take 2 times 26.98 plus, and then when I think about aluminum sulfate, I'm going to rewrite the formula up here. I'll get rid of my water. If I rewrite aluminum sulfate, I have to distribute the subscripts outside the parentheses into the parentheses. So what this means is I'm actually going to have 3 sulfurs and 12 oxygens. So when I add up the total molar mass, I'll take 2 times sulfur, 32.07, plus 12 times oxygen, which is 16.00. So when I type this all into my calculator, I get 342.17. So in my notes, my mass here becomes 342.17. Now I know that that has to go on my numerator, my top here, because I'm trying to cancel out the unit of moles. So I put 1 mole of aluminum sulfate on the bottom. This allows me to cross off the unit of moles, and I'm only in grams. Now, this number came directly from the periodic table, so we also consider that it has an infinite number of sig figs. So let me type this into my calculator, and then I'll slide that over, and we can check and see how to round this final answer. All right, so I type this into my calculator, and I get 119.7595. Now, when I look at my given number, 0.35 moles only started with 2 significant figures. And when I look at the infinite significant figures in molar mass, that means my final answer has to be rounded to only 2 significant figures. Now, this is a little trickier to round because it's 119.7. When I round this, it's actually going to round up, and I'm just going to make it the number 120. I don't put a decimal at the end because I don't want that 0 to count towards the number of significant figures. So I'll leave it as just 120. And then my units are grams of aluminum sulfate. Now the last step, the third problem here, is where we actually combine these steps together. We can make a problem longer by just connecting both conversion factors together. This one says how many particles and what type are found in 52.3 grams of carbon monoxide. So I'm going from grams all the way into particles. Now I can't go directly there. So I'm going to do this in 2 steps, actually. I'm going to first convert my grams into moles, and then I'll convert the moles into particles. So I'm going to write down my given, 52.3 grams carbon monoxide over 1. I'm going to want to convert this from grams into moles. Cancel out grams and convert into moles of carbon monoxide. And based on my knowledge of molar mass now, I know that 1 mole of carbon monoxide is equal to the molar mass of carbon plus oxygen. I know carbon is 12.01 for my periodic table. Oxygen is 16.00. When I add those together, I get 28.01 grams. So that's the mass of 1 mole of carbon monoxide. Now, grams cancels out. When I plug this into my calculator, I'm going to have to divide, but I can wait and do that step last. I'm going to do my other conversion factor first, and then I can come back and actually plug this whole thing into my calculator. Now my last step here, I want to cancel moles now. So I'm going to cancel 1 mole of carbon monoxide, and I want to get it into particles. This is where Avogadro's number comes in. I can use 6.022 times 10 to the 23rd. Now instead of particles, I want to try to use the actual term. We said carbon monoxide, that's 2 covalent compounds bonded together, or 2 nonmetals bonded together to make a covalent compound. I'm going to use the word molecules. So it's molecules of carbon monoxide over 1 mole. This allows me to cancel out the unit of moles, so now I'm left with molecules. Now, to type this all into my calculator, I can do it all as one long step. So let me pull out my calculator and I'll type that in for you. All right, so I type this into my calculator and I get 1.124 times 10 to the 24th. So I have to go back and think about significant figures here. My initial number, 52.3, started with 3 significant figures. My second value, 28.01, is the molar mass from the periodic table. I don't count that towards my significant figure, so I say that that's an infinite number of significant figures. I don't use it for rounding purposes. The same thing is true for Avogadro's number. So when I get to my final answer, I have to round it to match the same number of significant figures from my given, which was 3. So when I go back and look at my calculator, I'm going to write down the first 3 digits, 1.12. I don't have to round, and then it's times 10 to the 24th. 1.12 times 10 to the 24th, and now my units remaining are molecules of carbon monoxide. So this becomes my final answer. Hopefully this helped in setting up and solving some simple molar conversion problems. We'll be able to look at some more complicated problems as we practice this and get a little bit better.